To record already. So, like I said on my Canvas announcement, today it's going to be a fun time with Taylor series. Where we're just going to be doing a lot of problems with Taylor series. Or if we centered a Taylor series at 0, we're going to have fun with Taylor series' younger brother who just mooches off of him, Maclaurin. So I'll put Maclaurin in there as well. And essentially my goal today is just to kind of follow the same pattern that we've been doing for the previous few days. Do practice problems, and let's do it with Taylor series. So the first problem I'm going to do explicitly, and that's to give you all kind of the rough idea of if I'm given a brand new function, how can I get that brand new function and form a Taylor series around it. So for that example, let's say I want to form a Taylor series for the function 1 over x squared. And I want to center that guy at 1. And so let's figure out, if I'm just given this while walking on the street, how can I form a Taylor series for yes off the bat? Well, let's figure that out. Now, for yes, I want you to recall that all a Taylor series is, it is essentially the power series and a Taylor polynomial combined together, or the way I thought about it when I was learning this the first time, Taylor polynomials and power series had an ugly baby, and that ugly baby became a Taylor series. So the general form for a Taylor series is the sum going from k equals 0 to infinity. Now, just like a power series centered at a, I do have still the x minus a to the k power component. So that part's still the same from a power series. But the way that we combine a power series with the Taylor polynomial is, back when we just did a normal power series, I just wrote c of k for an arbitrary coefficient based off the index k. Well, for a Taylor series, the coefficients are now specific, and they are the coefficients that occur from a Taylor polynomial. So I'll go ahead and mark that there. These are the coefficients from a Taylor polynomial. And so our old faithful strategy to form a power series is going to be similar to how we form a Taylor polynomial. We're going to take a lot of derivatives, and let's see what happens. So for this, just like with Taylor polynomial, we're going to list down, to match these coefficients in pink, I'm going to list down f, I'm going to list out the first derivative, I'm going to list out the second derivative, so on and so forth. So first derivative is 1 over x squared. That's not surprising because I just read what the function was. First derivative. Like I said, you could be a madman and do quotient rule if you want. However, I'm lazy, so I'm going to do power rule. Give me minus 2 to the x cubed. And then second derivative, same idea. I'm going to do power rule again. That'll be negative 2, s to negative cubed. So derivative of that will be 6 s to the 4th. So 6 over s to the 4th. Third derivative of x. Again, that is 6x to the negative 4th. So the third derivative will be derivative of the second derivative, which will be 6 times 4, so negative 24 over s to the fifth. Let's make that clear that that's an exponent. And the pattern is going to keep on going like that. Oh, battery is running low, so let me grab the charger. There we go. So before we go on and do the evaluation of everything at the center, I do want to make an observation about the numerators for each of these f of x's. Well, 1 that's equal to 1 factorial. That's not super surprising because 1 factorial is just 1. Again, first derivative, I know I have a 2. Well, 2 factorial also equals itself. But in the second and third derivative, now I see the pattern because 6 is 3 factorial and 24 is 4 factorial. So that's something that I've noticed that I'm going to keep in mind when I'm doing this problem. To note that if I take a derivative, my numerator will be a factorial where the base is the next number over. So in this case, I'm taking second. So I expect the factorial to be the next base over, so 3 factorial. So I want to keep that in mind when I'm trying to simplify my Taylor series. So, but let's follow our noses and go ahead and do what we do for Taylor polynomials. Evaluate f at 1. Just get 1. Evaluate the first derivative at 1. I get negative 2. Evaluate the second derivative at 1. I get a positive 6. Evaluate the third derivative at 1. I get a minus 24, and so on. And I'm also going to keep in mind the observation that I had before. Let's put a negative up front. Keep everything in order. All right. So we have a general pattern of what our coefficients are going to look like. Let's figure out what the Taylor series looks like. Thus, the Taylor series is going to be the following. It's going to be f of 0 plus the first derivative. Oh, not Maclaurin. Taylor series at 1 over 1 factorial x minus 1. Not doing just x anymore because I have a center at 1 plus second derivative of 1, 2 factorial x minus 1 squared plus third factorial, evaluate at the center, 3 factorial, 1 cubed, and then I just keep on going forever. But since we did our work before, we could do some substitution. I know that f evaluated at 1 is just 1. I know that the first derivative evaluated at 1 gives me a minus 2. I know that the second derivative evaluated at 1 gives me 6, or 3 factorial. I note that the third derivative at 1 gives me minus 4 factorial, and then the pattern's going to keep so on. But I say we're going to do some cancellation. Because when I substitute in the second derivative at 1, it's going to be 3 factorial over 2 factorial, from what we talked about before. 3 factorial over 2 factorial is just going to give me 3 left behind. Same thing with the 4 factorial divided by the 3 factorial. From what we talked about before, I'm just going to get left behind 4, and so on and so forth. So after substituting and simplifying, I have 1 minus 2, s minus 1 plus 3, s minus 1 squared minus 4, s minus 1 cubed, so on and so forth. And we're going to try to write this into a series form. So one thing that helps me to write it out in series form so I'm going to list out what each term should be in the series. So in this case, 1 will be k equals 0. Minus the 2 times s minus 1 will be my k equals 1. The plus 3 s minus 1 will be my k equals 2. The minus 4 s to the minus 1 cubed will be k equals 3. So from this, let's make some notes for the pattern. So first note that I'm making is that the power that is with the x minus the center is going to match the index that is occurring. And that's true for k equals 0, because I could just rewrite that as 1 times x minus 0 raised to the 0 power. And anything raised to the 0 power just gives me 1. So there's my first observation or note that I'm making, is that the power with the s minus 1 component matches the current k. So there's this first observation. Now the second observation, and my second observation is going to occur with my simplified coefficients that I see there. So at k equals 0, my coefficient is 1. At k equals 1, my coefficient is a 2. At k equals 2, my coefficient is a 3, and so on and so forth. So the pattern that I'm seeing is whatever k is, I add 1 to k to give me whatever this coefficient is up in front of the x minus 1. And that's my second note. I add 1 to k to have the coefficient in front of the x minus 1 part. And so from these two, I can go ahead and start forming a skeleton of what my power series should look like. From observation 1, the power with the s minus 1 must match the current k. That's going to correspond to s minus 1 raised to the kth power inside my series. Now let's match with note 2. Note 2 is telling me I add 1 to k to have the coefficient that is in front of the x minus 1 term. And you're right, James. That means I'm going to have k plus 1. And let's give me some more space. All right, so let's say we have a nice series. We have a k plus 1 times s minus 1 to the k. Now my question is, am I done with forming that series or my Taylor series yet? You can reply with either yes or no. Yep, it will be something with the minus sign. Now, based on what you see, James, which values for k should have a negative sign up front? Bingo. And there's our third note from what we observed. Is that when k is odd, you should have a minus sign. And because it is the odd terms, that will be corresponded by -1 to the kth power. Now, if it was the even terms to have a negative sign up front, I would do -1 to the k plus 1 power if the even terms have a negative sign. But because the odd ones are the terms that have the minus sign up front, that means I'm going to write -1 to the kth power. All right, so now we have our power series for our Taylor series for this problem. But I'm not done yet, because just like with power series, I want to know the radius and the interval of convergence for this guy. And so let's find that guy. So first, let's find the radius of convergence. If it wasn't for that k plus 1, I would go strictly to root test right off the bat. But because I have that k plus 1 term, I'm going to go strictly to the ratio test. So before we start off, let's go ahead and copy down our AFK that we're going to be using. And now let's list down our AFK plus 1, which means wherever I see a k originally, I'm going to replace with a k plus 1. So x minus 1 to the k plus 1. And before we do anything, let's try to simplify as much as we can. K plus 1 plus 1, that's going to be k plus 2. And so now, finding the radius of convergence means I'm going to take the limit as k goes to infinity of a of k plus 1 over a of k, or the limit as k goes to infinity, absolute value of -1 to the k plus 1 times k plus 2 times x minus 1 to the k plus 1 power divided by negative 1 to the k power times k plus 1 times x minus 1 to the k power. And now let's go ahead and start killing some stuff off and simplifying. First, I have negative 1 to the k plus 1 power in the numerator, negative 1 to the k power in the denominator. So that gets to be simplified down to just a negative 1, which will vanish because of the absolute value. K plus 2 and k plus 1, I can't really do anything with that. X minus 1, in the numerator, I have an exponent of k plus 1. In my denominator, I have x minus 1 with an exponent of k. That can be simplified, leaving me with just x minus 1. Meaning what I have after cleaning up a little bit will be a limit as k goes to infinity of x minus 1 times k plus 2 over k plus 1. Note that I'm not including the negative 1 in my nets line because it's negative 1 multiplied by everything. So that negative 1 is going to go away anyway. So I'm going ahead and do that. Next step that we've done before, I'm taking a limit with respect to k, which means that s plus 1 is a constant. So I'm going to take it outside of the limit, but because of the absolute value, it's going to be the absolute value of x minus 1, because I don't know if it's positive or negative, times the limit as k goes to infinity of absolute value of k plus 2 over k plus 1. But because k is always positive, that means this ratio is always positive, which means the absolute value is redundant. And that limit gives me 1. So I have x minus 1 in terms of absolute value. And because I'm doing it with the ratio test, this will converge if it's less than 1, which means my radius of convergence is 1 because I have absolute value of x minus the center less than a positive number. So there's our radius. Now let's do the interval. So we're going to base this off of my radius of convergence. Absolute value of x minus 1 less than 1. That's the same as me writing negative 1 less than x minus 1 less than 1. And then my next step is add 1 to everything in that to give me 0, x less than 2. Which means so far my interval is going to be between 0 and 2. But now I need to check for endpoints. And check and see whether or not I can or cannot include them. So first, let's check if we can include s equals 0. If I plug in 0 to my power series that we have, I have negative 1 to the kth power, k plus 1. And at the x minus 1 to the kth power, I'm going to have 0 minus 1, let's stick with purple, to the kth power. After simplifying, I have the sum from k equals 0 to infinity of negative 1 to the kth power times the k plus 1. 0 minus 1 is just negative 1 raised to the kth power. I get another negative 1 to the kth power. Now, if I multiply those two together, what I'm going to get is -1 by my property of exponents. I add them together. So -1 to the 2k power, which means I always have an even exponent, which means that will always be 1. So after simplifying, I just have k equals 0 to infinity of k plus 1. And as Anthony mentioned, this series is going to diverge by divergence test. Because if I take the limit of k plus 1 as k goes to infinity, I'm just going to get infinity. And that's definitely not 0. So that means I do not include 0 in my interval of convergence. Now let's check and see if I can include, oh, I can't read today, if I can or cannot include 2 in my interval. So now I'm going to plug in 2 in my series wherever I solve the x, so 2 minus 1 to the kth power. 2 minus 1 equals 1. 1 raised by any power just gives me 1. So I'm just going to have the sum from k equals 0 to infinity of -1k and -1k plus 1. And I'll go ahead and let y'all know that this series will diverge again by the divergence test. The reason why I'll diverge again by divergence test, we talked about before, that guy's going to infinity, not to 0. And so because of that -1k power, that means I'm going to oscillate back and forth on the x-axis. So that implies the limit as k goes to infinity of -1 to the kth power times k plus 1 is d and e. Which means I do not include my right endpoint, which means my final interval of convergence for my Taylor series that I formed is 0 to 2, with not including the endpoints. And so that's going to be our kind of game plan for these types of problems. If I encounter a brand new function on the fly, I'm going to take a bunch of derivatives and show if I have a pattern. Now we're going to check and do some problems soon where we could cheat a little bit and go about that way. But there's an example that I walked through. Now it's audience participation time. And now y'all going to find a Taylor series for a function that I give y'all. Because now that y'all know the essential groundwork of how to run this bad boy, let's go ahead and give y'all a Taylor series to work with. Well, let's see, what will be a good one? So this one, if y'all seen the video, y'all know the Maclaurin series for e to the x? Well, now I want y'all to try to find the Taylor series for e to the x, where the center is now 2 instead of 0. Give you all about 10 minutes to work on that. And then we're going to work through this together and see what we got. And if y'all have questions, just like before, post them on the chat or unmute your mic, just go ahead and ask. All right, there's the problem I want y'all to work on. Go ahead and find that Taylor series and let's see what we got. And we'll reconvene in about 10 minutes when we're working on that. Give me a status report, guys. How's that problem going for y'all? All right, keep working on it then. Oh, I I got a message. Let me respond to that real quick. Oh, I see a message. Let me respond. Oh, just saw your most recent comment, Luke. In that case, I'm gonna let you finish. All right. See a couple of responses. Luke and James, I say that both of you have equivalent answers. James, a comment on yours. Since your index is k-1, when you write out your series, you would start your series at 1 and not 0 for it to be equivalent. But besides that, you both got it. Yep. So for the people who are starting to get the answer, what I want y'all to do now is find a radius and interval of convergence afterwards. Because when you come with a new power series or a Taylor series, it's a power series, so I want to know if it converges or not. And when you find a radius and interval of convergence, also post that on the chat. I'll give y'all about like another minute or two, and then we'll go over the solution or how we got the solution. All right, let's go through the solution. You could, James, post the solutions on the chat, but I want to go through also how we get the answer. So first thing to note, since we're working with e to the x, I think by now we could go ahead and just say that e to the x is the most boring function ever in terms of derivatives, because the derivative is itself no matter what. When I evaluate that, 2, I get e to the second. Unique, depending on, it depends on what you mean by best. But anyway, since we now always have a coefficient, if I write out the Taylor series explicitly, we have f evaluated at 0, which is e to the 0, e to the 2, plus e to the 2 over 1 factorial, x minus 2, plus e to the 2 over 2 factorial, s minus 2 squared, and so on. And if this is corresponding to k equals 0, k equals 1, k equals 2, and so on and so forth, I now have the sum from k equals 0 to infinity of e to the second power times x minus 2 to the kth power divided by k factorial. James, I'm going to take a guess as to how you got k minus 1. Did you dot of e to the second as k equals 1? And this is k equals 2, k equals 3, and so on? Yep. And that's perfectly fine. Just like I made in my comment, if you do that, just make sure that you start your series at 1 to adjust accordingly, which is what you did. Yep. All right. And now let's figure out, since I have a brand new series, what my radius of convergence is. Quick poll. How many of y'all went ahead and figured out what the radius of convergence was? And if so, what did you get for the radius? It's not quite unique. It's not going to be 2. Let's go ahead and figure it out. Because I see a factorial, the test I'm going to choose is the ratio test. So let's just tell a of k. and a of k plus 1. And now let's do that bad boy with calculating the limit of the ratios. So limit as k goes to infinity of a of k plus 1 over a of k equals the limit as k goes to infinity of a of k plus 1 times the reciprocal of a of k. Now a lot of stuff gets to die off. First, e to the second gets to die off. K factorial in the numerator dies off, and the k plus 1 factorial simplifies down to just k plus 1. The s minus 2 raised to the k plus 1, s minus 2k, that's going to simplify down to just s minus 2. And then after cleaning up, we have limit as k goes to infinity of x minus 2 times 1 over k plus 1. I'm taking a limit with respect to k, which means the x minus 2 is a constant. That's going out, but because I'm inside the absolute value, it's going to be absolute value of x minus 2 times the limit as k goes to infinity of absolute value of k plus 1. But since that's positive, that is redundant. But this limit equals 0, which means the whole thing equals 0. And that's definitely less than 1. Now, we did an example. If y'all were here yesterday, we did something like this yesterday during our Zoom meeting. If I was trying to find a radius of convergence and I got that L equals 0, how can I interpret that? That's my question for y'all. How should I interpret when I'm trying to find a radius of convergence? I just have L equals 0, which is always less than 1. Bingo. The radius is infinity because the way that I get to interpret what Gits tells me if I get 0 is that my series will always converge no matter what value of x I plug in, which means my radius of convergence is infinity. And because my radius of convergence is infinity, that means my interval of convergence is any real number that I could think of. All right, and there's that bad boy now taken care of. Now with that, if y'all have any questions about that, again, post it on the chat. And while you do that, I'm going to go ahead and write down the next problem that I want y'all to find a Taylor series of. Hmm.
I have a quick kind of general concept question for interval convergence.
Okay.
So I was doing the MATLAB for what was it, 11.2 today. When it comes
Mhm.
to natural log functions, there seems to be the pattern of the left-hand side usually converging.
Mhm.
Are there any more distinct patterns that creep up between just parentheses and then one definite left-hand bracket when doing these types of problems?
It depends on the function you're working with. Natural log, that's one of them. Um, and then there are other cases of functions where that's the case. But I would say it's too broad to say, for example, if I have an odd function, the right hand side is going to be closed or left hand is going to be open. It's a little bit more specific than that. So for natural log, it inherits that behavior, but it's nothing in the sense that, oh yes, whenever I see this big class of functions, I can do it. So,
Okay, you're right, and that was a really broad question in general. The other one was building the power series
mhm.
of getting to that e squared times x minus 2 to the k.
Yep.
Oh wait, no, I figured it out. Never mind.
Oh, glad I could help by scrolling up.
Yeah, yeah, no, it's x minus a. Okay, yeah, that makes sense. That's all I have.
Alrighty. And like I said, I think this is the chapter where the rubber meets the road, as we're essentially putting everything we learned together. So, I found a bad one to work on. Log base 3 of x plus 1. And I want y'all to find the Maclaurin series of that. And here's going to be, yeah. And for this one, I'll actually give y'all a hint. Y'all could do the old-fashioned way of how we tackle it. But keep in mind, our normal change of basis formula. And that's going to be the hint I give y'all for that problem. Is think of rewriting log base 3 of 1 plus x as the natural log of x plus 1 over natural log of 3. I'll give y'all a few minutes to work on that. And if y'all have questions, post them on the chat.
Wait, I have another question.
Okay.
With this adhering to our natural log of 1 plus x formula, wouldn't that be the series where with negative 1 to the k plus 1 x to the k over k, just with adding a constant of 1 over ln 3?
That's why I gave the hint.
Nice.
Yep.
Also, Yannick looks very handsome today, I'm betting.
All right. And also with this, I want to make y'all a note. I want y'all to find the radius and the interval of convergence as well for that guy. Oh, Anthony, to answer your question, sadly, I don't know. Knowing Dr. Burr, is probably going to be no for stuff like log base 3. Um, however, I don't think she'll be mean enough to put a question like that on the test where it's going to be nasty to do the long way but not so bad if we do a change of bases type of scenario. And respond to this message on the chat. Oh, all right. So I think that thanks to the hint, I think a lot of y'all have the answer right now, or for the series. Am I right on that? Well, in that case, I'm going to go ahead and do the solution for his problem. Like I said, for a Taylor series, you could do the alpha way of doing it, which is take derivatives over and over again. That's sort of our standardized last resort, but there are ways we can cheat around that. And the ways I'm going to cheat around that is note that for log base 3, I could do a change of basis formula and say that's equal to natural log of whatever is inside that log base divided by natural log of the base that I'm working with. And the reason why I want to work with that is because at the end of section 11.3, natural log of 1 plus x, or x plus 1, those are one of my series that I know stuff about. And the power series representation for that is the sum when k equals 1 to infinity of -1 to the k plus 1 s to the k power over k, where the interval of convergence is -1 to 1 with a closed bracket on 1. The reason why it's a closed bracket on positive 1 is if I plug in 1, I'll get the alternating harmonic series, which we proved in the very beginning of section of alternating series that is convergent. And if I put in k plus -1, I'll get my harmonic series. But natural log of 3 is just a constant. So I can rewrite that as k equals 1 to infinity of -1 to the k plus 1 power, that's to the kth power over k times natural log of 3 as my power series representation for that problem. Now, forgets, here's my question. Forget's new series, would the interval of convergence be different? Yes or no? Luke and Isaac, I agree with you. Luke, I like that you put a question mark to be like, eh. But no, I'm not trying to trick you here. The answer is no. And the main idea you could think of is, it's a constant factor or a common factor with each term in my series that's not being altered by the index k. So if I have that common factor, I'm not going to change my radius nor my interval of convergence. So that's a neat property that we're going to note. That multiplying I know we're talking about Taylor series, but I'm going to be more broad and talk about power series because the same property applies for a power series by a constant does not change the radius of convergence or the interval of convergence. Which means that with our brand new series, we still have that the radius of convergence is 1, and that the interval of convergence is -1 to +1 with a closed brace over to 1. And boom, there's one way that we cheated from having to do our good old faithful method of taking derivatives to get the coefficients for a Taylor series. Make the observation I could rewrite f of x, use a Taylor series that I know, or in this case, a Maclaurin series, and go about it that way. And I say for the next example, for the next problem, is going to be very similar. 2 1 minus x cubed, where a equals 0. That's going to be the next problem that I give y'all to work on to find the Maclaurin series for. And while y'all could do the old faithful method of finding the coefficients for the Taylor series, for the Maclaurin series, I want y'all to keep this in mind either. I say that f of x has a relation with 1 over 1 minus x. And so when y'all worked on that, on this problem to find the Maclaurin series, figure out what relationship we share with f of x and 1 over 1 minus x. I'll give you all about a quarter till 5 before we go tackle the problem. And don't say antiderivative, Anthony, because antiderivative of 1 over 1 minus x will be negative times the natural log of 1 minus x. And I don't see a negative, and I don't see a natural log of that f of x. Yeah, I know y'all did. But no, and I agree with y'all, with you, Anthony. That is the second derivative. And so now we can abuse our that to power series of taking derivatives of a power series. I'll be right back. Give me about a minute. How's that problem going for y'all? All right. Not quite, Isaac. Um, Call it the power series of 1 minus x, a 1 over 1 minus x. And as Anthony mentioned, the function that we're finding the Maclaurin series for is the second derivative of 1 over 1 minus x. And this has the Maclaurin series. Oh, already. So you're not going to get x to the 3k power. All right, I'll give you all about another 2 minutes to work on it, and then we'll go through this together. All right. So, what did y'all get for your Maclaurin series for that problem? Y'all don't have to write down the sum portion. You can just write down what you have for your term within the series. Actually, let's put this up here in purple. All right, let's ask again. Based on what you currently have so far, what do you have as your Maclaurin series for 2 over 1 minus x cubed? Anyone there? Can anyone hear me? Silence. Oh, there we go. All right. In that case, go ahead and type down what you have for your Taylor series. Oh, thank you for being honest, Unique. We'll go over the method of how we do it. Just go ahead and type down what you currently have. Yeah, I'm not gonna lie, Unique. That's pretty. It's pretty far off. How we get our answer shortly. Anyone else? All right. On that note, go ahead and do the solution. So as Anthony mentioned before, this is the second derivative of 1 over 1 minus x. The power series representation for, or the Maclaurin series for 1 over 1 minus x is x to the kth power. All right. And so our property of power series tells me that when I'm taking a derivative, I can move that derivative and take it term by term. And so let's do that real quick. And let's do that on the side. First derivative, of x to the k by power rule, give me k times x to the k minus 1, which means the second derivative of x to the kth power, which will be the first derivative of k to the k minus 1, will be again by power rule and constant multiple rule, k times k minus 1 times x, k minus 2. So what I get inside my series is the sum from k goes from 0 to infinity of k minus 2 x to to the k minus 2 power. Or k minus 1. Whoopsies, there we go. And that's what I got from my power series for that. Keep in mind that, take a derivative of a Taylor series. I could do the exact same mentality as I would for derivative of power series. Same with integral of Taylor series as well. And keep in mind that one of our properties of taking derivatives or integrals of Taylor series or power series still applies here. Is that the radius of convergence is still maintained, meaning I keep the same radius of convergence as the original series that I was working with. Now, as for the interval of convergence, keep in mind, let's go ahead and change some stuff up real quick because I just noticed. The index will be 2. The reason why the index will be 2 is because I'm taking 2 derivatives. And for a power series, whenever I'm taking a derivative and a derivative again, I'm just keep on taking and moving my index to 1 and to 2. Mainly because when I take a derivative, I'm losing one of my terms because one of my terms is a constant. And derivative of a constant is 0. And since I took the second derivative, that's why my index now is going to be 2 instead of k. Does that make sense for everyone? Why I'm starting at 2 and not 0 for my power series? For my Maclaurin series? All right. So unique says 2 a degree, so let's go over that real quick to make sure we're on the same page. So the reason why we're starting off and we're starting at 2 instead of 0 is because when I'm taking a derivative of a general power series, if I expand this out explicitly, at k equals 0, I'll have C0, x minus a to the 0 power, plus C1, x minus a, plus C2. Let's go ahead over here. X minus a squared, so on and so forth. Now, because the x minus a to the 0 power, that's just going to give me 1, which means I can rewrite that as the derivative with respect to x of C0 plus C1, x minus a, plus C2, x minus a squared, so on and so forth. And now because for C0, this is a constant with respect to x, derivative of a constant will be 0 once I do that. Meaning, after I take derivative of all of this term by term, and that's exactly right, Unique, because I now start at the next one, which will be C1 plus 2 times C2, s minus a plus 3, C3, s minus a squared, dot, 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 which is why we have our formula for the derivative to be at 1, CFK times k x minus a to the kth power. And because I do that, I'm taking the second derivative. That's why I'm starting at 2. All right, good. Good, I'm glad I helped you. So now we started at 2. I'm going to make a note at the end of what a lot of people do with series, myself included. But let's go ahead and finish this problem out. So your series has the same radius of convergence, but when I take a derivative or integral of an arbitrary power series, which falls under Maclaurin series as well, I'm not necessarily guaranteed that the endpoint behavior is going to be the same. Luckily for this problem, the end behavior will still be the same, because if I plug in -1 and 1, or 1 into my new series, I'm going to get divergence by the divergence test. If I plug in +1, I'll have k minus 1, which goes to infinity. If I kept plugging the -1, then because the positive terms go to infinity, the limit will not exist. So that's why my interval of convergence is still -1 to 1, open parentheses. But before we head off, I'm going to make a quick note. And as with my index at 2 for this problem, so this is related to the comment that I made to James when he posted his solution earlier, when he had the k minus 1, and I said start your series at 1 to be equivalent. The reason why I say that is I can actually do something called a change of variable. The analogous thing that y'all can think of for this is a u-sub. But when I'm using it in this case for a series, I am essentially going to change the index of my series. And here's how I'm going to do that. If I'm going to change the index of my series, then my thought process is as follows. Right now, my series starts at 2. So I'll write that down. Right now, it starts at 2. What I want is for the series to start at 0. And so here's how my thought process is. Well, right now I have the relationship that at the beginning of my series, k equals 2. And so if I want this to start at 0, what my thought process is I'm going to subtract 2 from both sides, and I'll get k equals 2 equals 0. And this is where I mean when I say I'm going to do a change of variables to force my series to start at 0. I'm going to define a new index, and it could be whatever you want. In this case, it's going to be n. I'm going to define n to be k minus 2, because I note from the start of my series, k minus 2 equals, if k equals 2, and k minus 2 equals 0. And so let's check how that's going to change our series. Well, if k equals 2, that means n equals 0 for yes. And now within my series, wherever I saw a k, I'm going to rewrite it in terms of my brand new change of variables k of n. So right now, excuse me, I see a k minus 1, and a k minus 2. Well, since k minus 2 equals n, I could change that exponent very quickly. But right now I have a k minus 1 and then a k. Well, if I define n to be k minus 2, then adding 1 to both sides, right, that gives me n plus 1. Yeah, no, Unique, I agree with you. It will be k plus 1, n plus 1. And now for that k, if I do it again, add 1 again to it, I get n plus 2 equals k. So for this problem, I could have kept my original series, the sum going from 2 to infinity of k minus 1, and then x to the k minus 2 power. But keep in mind that I could always do a change of variables within my series, force my series to begin at 0 by essentially asking, okay, my series start at 2, how can I force it to start at 0 or force it to start at wherever I want it to start at? And this is our methodology in order to accomplish that. And that was why when James posted his solution to the first example I had y'all work on, I said that his answer was correct, even though he had a k minus 1 instead of k. Because then I'm assuming that his series started at 1 and not at 0. But he could transform it very quickly by doing that change of variables where n is k minus 1. Does that make sense to y'all? Alrighty. And that's not something that is mentioned in the Briggs textbook, which I do not like. And so in that case, I want y'all to be aware that, yep, technically, I could start wherever I want and do a change of variables, or another way you could take up this method is I'm shifting where my series is going to start. All right. That's all I got for now for today. Any last minute questions for me before I end our fun time with Taylor series for today?
Oh, wow, that was pretty fun. I do have one more question.
Go ahead.
So when it comes to putting out all this together, would you still recommend going over like practice exams for exam 3? Or is the content kind of
I would recommend that because since we don't have a test 3 anymore, Dr. Bird did make it clear that uh, for the final, 70 to 80% will be the stuff after test 2, since
Mhm.
we have not been, since y'all will not be specifically testing on that material. See you,
Okay.
Anthony.
Alrighty, that makes sense. That's all I have. So thank you.
Alrighty, we'll do this again tomorrow.
Have a great
All
day.
right. All right. You too. Bye.